Okay, so the most important thing about atmospheric physics, Pato, is we're dealing with the gaseous atmosphere. Now, it's a gaseous atmosphere, gases held within a force field. The force field being gravity.
Yeah.
So we only have one side, which is solid, held within a force field. Now, gas laws are very different to laws with solids or liquids. They are different beasts. So they don't work anywhere like what you've imagined or what you've been taught in school or even university. So to understand gas laws, that's what we're going to deal with right now. And if you understand gas physics, then you can truly understand meteorology. Without gas physics, you can't truly understand meteorology. Okay, so the first thing is we have gases. What is the composition of the atmosphere? Because we need to know this to understand the beast we deal with.
I did know it, I don't know it anymore.
Okay.
It's like nitrogen.
Let's try nitrogen. It's actually N2.
Yep.
Let's go oxygen.
It's like 6%, huh?
Let's go argon.
1%?
1%. Let's call this one 21%.
Yeah.
Now I'm rounding these numbers, so they're going to come up to be above 100% because I'm rounding up. Let's call nitrogen 78%.
That's always the big one, yeah.
99% of the atmosphere is nitrogen and oxygen. 1% here. Now, CO2, this is the beast that everyone's scared of, that's talked about all the time and is so instrumental in supposedly deciding the temperatures of the atmosphere. So it said, what's the percentage of CO2?
Minuscule.
0.04%. And there's a fifth gas, which is the most important gas. Now it goes above 100%. Don't concern yourself with that. There is a fifth gas, the most important gas, to determining the weather. H2O. Water vapor. The percentage of that can vary between, let's call it 0%. I'm being aggressive. It's probably always got a bit of water vapor in the air. To 5%. That's about the max. You know, when I say 5%, that'd be very extreme, stuff like that. But let's call it 0 to 5% absolute, not relative humidity, absolute. So, this is important. Here are our gases. And to understand what we're dealing with from a scientific sort of point of view and from a meteorology point of view, surely we need to understand what's actually in the damn atmosphere to begin and what each of these guys can do. So let's have a look at that. Now, one of the rules of gas physics is this. If we take a cubic meter of gas, so 1 cubic meter, doesn't matter what kind of gas, doesn't matter what kind of molecules, doesn't matter what blend of molecules or blend of gases or whatever, at the same pressure, volume, temperature, whenever we describe a gas, we must describe pressure, volume and temperature because that determines the size and the density and weights and things. There will always be the same number of particles in that square cubic meter. So no matter what type of gas, no matter what blend of gases, at the same pressure, volume, temperature, we will always have the same number of molecules. If we take this box and water vapor evaporates into that without changing its pressure, volume and temperature, will the weight of that cubic meter of air decrease or increase, and why?
Water vapor.
Yeah, so water vapor evaporates, goes up into, this is a box of air directly above the ground, it evaporates into that.
Decrease, will it?
And if it decreases, why do you believe it decreases? Because we've added water vapor up here. I gave you a couple of rules, Avogadro's rule. I'll give it to you. Now, if water vapour comes up here, and we go, oh, it gets lighter. Why would it get lighter? Because if we're adding water vapour to the box, surely if we add something, it would get heavier. I'm going to go through it with you, just for kicks. Okay, what we need to know then is if we have gases, and here's the key, they've got the same number of particles
No matter what.
every time, no matter what, at the same pressure, volume, temperature. Maybe there'll be a weight difference if these bad boys have different molecular weights. Now, I'm going to give you the molecular weights. I'm going to give you a molar weight, don't worry about anything else, but they'll just be numbers, so it's a relative issue. Let's call that 28 grams, let's call that 32 grams, let's call that 40 grams. CO2 is the heaviest at 44 grams, and H2O, water vapour. Remember, I'm always going to define water or water vapour, because water vapour acts differently to water, 18 grams. So from those different weights of those gases, which do you think is the lightest?
Out of all of it, the water.
Out of all those ones.
Well, I'd probably go up to 18 grams. So,
Correct.
Yeah.
Water vapour. And the heaviest is?
44 CO2.
Correct.
Yeah.
So the majority of the atmosphere is here, 28 and 32. So when we do our calcs, the general weight of the atmosphere is about 29 grams relative to all that.
Yeah.
Now, that's just a relative thing. It's called molar weight. Don't worry about it. But we can see water vapour is not just a little lighter, it's significantly lighter. Significantly lighter. CO2 is heavy, argon's heavy, but the majority is right here at about 29. Okay, so this becomes important. So let's go back to our box. We have a box, metre cubed, and we're going to keep it at the same pressure, volume, temperature. And therefore, it will always have the same number of particles. So if we evaporate water vapour into this box, what must happen? Keeping the same pressure, volume, temperature. Other particles must leave.
Yeah.
So therefore, we replace heavier
With the lighter.
particles with lighter particles. So if we add water vapour to a parcel of air, assuming we keep the pressure, volume, temperature the same, that parcel of air, box parcel, will become lighter. Now, this is an important thing. So, let's say we take, and we know this thing, let's say we take a hydrogen balloon. Hydrogen's actually H2, let's say it weighs 2 grams. What direction, when you drop your hydrogen balloon, does it go? Hydrogen balloon. Up. We have a helium balloon. I think it's 4 grams.
Same thing.
If we drop our helium balloon, which direction does it go? Up. If we take a basketball, take it across to the pool there, and we shove it down to the bottom, which way is it going to go? Up. Now when it goes up, does it go up at a velocity, or does it violently try to accelerate? Violently tries to accelerate. So what we're looking at now is a very important thing. We just don't have a velocity, we have an acceleration. So not just a velocity, an acceleration. This is critical because at all times our atmosphere has a force working upon it which is
Gravity.
an acceleration. And the acceleration is 9.8 meters per second per second. So that's not a constant speed, that is an acceleration. Remember, force equals mass times acceleration. Force does not equal mass times velocity. Without an acceleration, we can't have a force. So these are critical things. So what is called is we have a hydrostatic atmosphere, which means as we go up in that atmosphere with greater attitude, 2 main things occur. Temperature decreases, and let me add this, in the troposphere, not the stratosphere, the troposphere, and the density of air decreases. The pressure decreases, the density decreases, the temperature decreases. So we're happy with those ideas. If we're in a jet plane doing 40,000 feet, the temperature is probably minus 60 degrees. It's never 44 centigrade boiling. It's always minus 60, minus 50, minus 40. So we know near the ground we can get to 30, 40 degrees in the day, 20 degrees. At that height, it's never that temperature. So let's have a look. Let's go further. Now we're going to have a look at water, because water determines our weather and it fuels the energy behind the movement of air in the troposphere. H2O. Water. Not water vapour, water. Now there's something called specific heat. What specific heat is, and I'll keep this simple, is if you take a quantity of a substance and you want to raise its temperature by 1 degree, it requires a certain amount of energy. So with water vapour, let's say we have 1 gram, which is 1 cubic centimetre of air. We want to raise its temperature by 1 degree centigrade or Kelvin. We need to input a certain amount of energy. Do you know how much?
No.
So we want to raise it from, say, 1 degree to 2 degrees. The answer is 4.2 joules, and I'm going to change for convenience to imperial, 1 calorie. So funnily enough, our counting system and measurement system has been designed about a gram of water to a cubic centimetre. To raise it by 1 degree requires exactly 1 calorie of energy. Pretty convenient. So let's say we have 1 gram, we want to raise it from 20 degrees to 21 degrees, so there's a 1 degree difference. How much energy do we need to input?
Well, going off that, it'd be 1 calorie, but as it gets
correct.
higher, it gets...
Don't worry, 1 calorie. Don't get too tricky. There will be a trick later. We'll get you on. 42 degrees to 43 degrees. How much?
It looks like 1 calorie, but...
You got it.
Yeah. I'm starting to think that as it gets higher, you might need more, but...
Yeah. In water?
Yeah.
No, I've given you the answer.
Yeah.
So, 93 degrees to 94 degrees.
Same thing.
Okay, nice. 99 degrees to 100 degrees.
Yeah.
Nothing's changed.
Yep. Still
1
1.
calorie.
But is there a point where you get...
Here is the trick. 100 degrees to 101 degrees. Wait a sec. And we're going to go from water to water vapour. So we change phase. So we're changing phase. How many calories? This is called latent heat. It'll be hidden. In fact, it's hidden there. We don't actually... It'll actually change phase staying at 100, but just for kicks I'm adding on 1 degree.
Yeah. So at that stage it's going from water to water vapour.
Yes.
So there must be a massive amount, or...
2 calories, 10 calories, 50 calories. The same amount, 1 calorie.
I think there'd be more calories as it gets up. I don't know the answer. Let's say 10. Probably too many. Ooh.
Now,
wow.
look at that.
540.
This is really important. If we want to heat water by a degree, a calorie of energy disappears into it and we get a temperature change. In fact, this doesn't need to be 100 on 1. Let's keep it at 100. It's 540. It hasn't changed temperature. It's changed phase. 540 calories of energy, which is heating that water from 0 to 100 degrees 5.4 times, has disappeared into there without changing temperature. So this is important. Just because we put energy into something does not mean we change temperature. This is critical. Just because energy and sunlight pounds into something does not mean that it necessarily changes temperature. Now this, in this phase change, is called latent heat, hidden heat, hidden energy that you can't see. And this is the energy hidden in water vapour that drives all of our weather that exists. It is stupendous. Stupendous. Now, let's move on. Each day we have the sunlight coming in through the Earth's atmosphere. Let's say we have west launch going down to the river beam just behind the house there, about 200 metres. There's the mountain. Let's call it east launch. Now, the sunlight comes down. Here's our atmosphere. This is critical. As that sunlight comes down, as the sunlight comes down, does it heat the oxygen in the atmosphere? How does our atmosphere heat? This is the question I'm looking at. Because obviously the air's warm around us. It's probably 20 degrees at the moment, 23 degrees around us. Is that sunlight heating that oxygen?
It hits the earth and then releases up through that one.
Sure, that's a good method. So,
It's
is it heating the oxygen as the sunlight comes through? In the troposphere. I'm staying with the troposphere. I'm ignoring the stratosphere at the moment.
Cools down.
The answer is no. Does the sunlight heat your nitrogen in the air? Your answer is no. Does your sunlight heat the CO2? Remember, this is the beast, the radiative gas. Everyone jumps up and down about, does it heat the CO2 as it comes through the air? Your answer is no. Does it heat your argon? No. Beautiful answer. Does it heat your H2O water vapour? No is your answer. Love your work. Now, as you mentioned, that sunlight hits the ground. Now, we definitely know that the sunlight heats the earth. We know the sunlight heats water. And when that heats, it then gives off IR radiation. And this will start going up. Now, with this IR radiation, does it heat the oxygen? Love your answer. No. Does it heat the nitrogen? No. Glad you asked. Does it heat the, let's go to the argon. Does it heat the argon? No, it doesn't. Heat, change the temperature of. Change the temperature of. I'll be very accurate. We'd say heat, change the temperature. Now, these two little guys are called radiative gases, and then you'll hear about this guy all the time. Does it heat, change the temperature of the CO2? Great answer, no. Does it change the temperature of the H2O water vapour? Your answer again, love your work, first person ever, no, to get it all right. So if this is not happening, how the hell is our atmosphere near the ground heating or changing its temperature? Three ways before we get into physics is radiation, let's do conduction. You know what conduction is? You have a hot plate, put your hand on it, directly touching something, it will burn your hand. It will conduct that energy through. But if you have your hand a long way away, it's not conducting, you will be okay. If you put your hand near the hot plate, you can feel radiation. So we know the difference. There's one more, convection. Convection is when you have a parcel of fluid that moves through a fluid in a hydrostatic system. That means there is a temperature gradient difference. Now, let's have a look at how materials act. Because we've never looked at this. They didn't teach this at school. I don't know if it's a conspiracy or just a fourth-rate education in Australia, but let's have a look. Solid, liquid, gas. We've just had a look at this. Can radiation heat a solid? Okay, what we're going to do here is we have sunlight coming down outside, and this is very important. Let's have a look here. We have some shaded concrete. We have some concrete in the sun. I have a road over there which is in the sun. I have some grass which is in the sun. I have some grass which is in the shade. I have a tree trunk in the shade. I have a tree trunk in the sun. I want you to go outside and put the back of your hand on each of those different things, both the grass in the sun and the shade, the concrete in the sun and the shade, the road, the plant, the trunk, and come back and tell me if you can tell the differences just with the back of your hand of those things which are being heated by the sun. So I'll give you a couple of minutes. So I want you to do some empirical. So what do you think?
Yep.
Significant differences?
Yep. Radiation.
So solids, depending on the amount of sunlight they get, how long they get it, how perpendicular that sun is, shaded or not, there will be significant differences in temperature. It's very obvious. Now the same occurs with water, but to a lesser degree. I'm going to show you the difference. So, if we have this solid heating, let's go back to here. The solid, can it heat by radiation? Yes?
Yes. From the sun.
Can a liquid heat by radiation? Can water be heated by the radiation of the sun? Yes. We've just gone through the gas. Can a gas be heated by radiation? No. Now we're talking about the normal temperatures on Earth in the troposphere, not the stratosphere, etc., etc. Conduction. Can a solid be heated by conduction? You put your hand, which is a solid, against a hot plate. Yes. Can a liquid be heated by conduction? You put a liquid against a saucepan. Yes. Can a gas be heated by conduction? You put a gas near something hot. Yes. You put it directly against something. Yes. The heat will conduct in. Let's have a look at convection. Can a solid convect? No. The solid just sits there, it can't move. Convection is movement of a parcel. Can a gas convect? A thermal convex moves up. So long as we believe there's thermals, then we have movement of particles through the air. Gas can convect, and a liquid is a fluid, just like a gas. We have cold parts and warm parts of parcels that move through the liquid. So yes. So look at this. A gas cannot heat by radiation. Conduction works on solid, liquids and gases, but a solid cannot convect, only liquids. But this is important for our gases. A gas cannot heat by radiation. So, to heat the atmosphere in the troposphere, the only way we can heat the gas is through conduction. We can actually do it through convection, but we need a heating source in the first place to heat the damn thing. So before we get our convection, we must have a heating source, which is a solid or liquid, and therefore we're heating the atmosphere through conduction. So if the heating source is the ground, where will you find the greatest temperature in your atmosphere? Nearest to the ground. And as you get further and further away from a heating source, you stand further and further away from a fire, do you get hotter or colder? You get cooler. So we could safely assume that as we move further and further away from our heating source, the temperature should decrease. Sound fair? Very simple thing. So our heating source is not the sun directly, it is indirectly the sun, but it is the ground or liquids which will heat our atmosphere. And you can see, depending on what the object is, it could be rocks, it could be grass, it could be concrete, it could be metal, it could be a tree, it could be a mountain, all blends of things, it's going to significantly change its temperature, relatively speaking, and create vast differences in heating of those gases above it. Now, we've talked about some of these things. As you can see, this is critical to understand these things, to properly understand meteorology. And if you don't understand this basic atmospheric physics, at no point could you possibly begin to understand meteorology. Whereas a lot of people may believe they do. Now, the atmosphere structure, no matter what anyone thinks, its temperature structure has a very simple equation. And we're going to jump backwards and forwards on things as we develop our atmospheric ideas. Now, there is something called a dry adiabatic lapse rate, which I'm sure you've heard about. Dry adiabatic lapse rate for short. And what is that dry adiabatic lapse rate? It is 9.81 degrees per 1,000 metres, give or take. I'm being a little exact. Some people round it to 10 per 1,000 metres. Some people use feet or stuff, but I'm going to use this. I am going to use this. Now, 9.81 dry adiabatic lapse rate of our planet's atmosphere. What does that 9.81 remind you of that we touched on earlier? The acceleration of gravity, 9.18 metres per second. Do you think that is a crazy coincidence, or there could be some relationship? What do you think?
Oh, it's connected.
CP. CP is your specific heat. Remember, we touched on the concept of specific heat. Meter cubed of air. So, to raise a meter cubed of air by 1 degree, that's what that is asking, the energy will be 1,000 joules approximately. It's 1,003, but we're just going to round it. Gravity, 9.81. So, the temperature structure of our atmosphere in the troposphere on Earth is determined by the acceleration of gravity over the specific heat of a meter cubed of air. This is profound. The dry adiabatic lapse rate, or the decrease in temperature as a parcel of air ascends in the atmosphere, the temperature change is determined by a speed. The speed or the acceleration of gravity determines temperature. Speed determines temperature with force using acceleration. Now, let's have a look at another funky little equation that people have probably not thought too much about. E equals mc squared. Do we know that equation?
And it's energy equals mass times squared.
Light squared. Okay, speed of light squared. So, we had to think about that. That's Einstein, he cranked that out. Let's have a think. We just found out something profound. Our temperature of our atmospheres decrease as we go up is determined by a speed of the force field around it, the acceleration of the force field around it. Energy, the amount of energy is determined by a speed. Mass on, well, let's do this, energy on mass is determined by speed, or mass is determined by speed. Pretty profound. So, if we know that now, do we need to understand that speed is instrumental in determining temperature, energy, and mass? And if we ignore speed or acceleration of force fields or anything else, we really don't understand much. I'll leave that with you just as a side note and something to ponder before you go to sleep. Now, let's have a look. We always draw this diagram, call that east launch, come down here. Let's call this the river, which is just behind us down there, east launch. Now, we can see that we have a slope down and then we have a slope down here. So what we call the flatlands are not actually flat, they're actually sloping. Now if we look out this window, we can see where the river is. It's a tree line back behind the house there, about 200 metres. Now, funnily enough, that is the lowest point in the valley. That is where the water is. Because water will find the lowest point it can at every single point. This is critical. If we have a water flow and it wants to get over there, it doesn't go there. It will choose at every point the lowest decline to get to that point. At every point. It won't go up first, then go down. It'll choose the lowest possible route at every vector. This is critical. Let's say we take our hydrogen balloon and we let that hydrogen balloon go on this roof in here, which is a pitched roof. And we left it for an hour. No matter where we let that balloon go, it would end up where? Directly above your head at the high point. So that hydrogen balloon, which is a lighter parcel of gases in our atmosphere, tries to get to the highest point at every instant. You never need to look at the lowest point because it just won't be there. It doesn't want to be there and it won't be there. There's no use looking. This is critical with probability distributions of what we're looking at with thermals. There is no use wasting your time looking for a balloon at low point, or if you knew nothing about general physics or what the balloon does, you'd spend your time looking at every point rather than just going to exactly what it was. With the water, we're not going to find it on top of the mountain unless we have a dam. If we don't have a dam, we're going to look for it at the lowest point in the valley. There is no point looking for it anywhere else. Or if we're looking at the mountain, we won't look for the spurs, we will look for the valleys for where the water is. This is critical. Sounds obvious when I point it out. Now, this is another interesting little thing. Let's say we have our heating source, which is the ground, and it starts heating up a parcel of air above it. What happens is this. When we talk about a thermal, we know this. We know the thermal is a separate parcel of air to the air around it. But this seems to clash with what we were taught at school. When we put a couple of gases together, they mix. If we put gases together, they mix. And they're always mixed, and they're always perfectly mixed. We don't walk around on Earth and go, oh my God, just ran out of oxygen in that little bit of air, I better return to this air. It's always mixed. But the thermal isn't mixed. It's a separate parcel of air. Well, unless you believe that the thermal exists as a separate parcel of air. Now we know the sailplane guys know it. We know the glider pilots know it. We know the hang glider pilots know it. We know the paragliding pilots know it. Nobody else knows it. That we're trying to catch parcels of air that are separate to the air around them. They're not mixing. They're remaining separate. Now this is called adiabatic. What does adiabatic mean? It does not mean anabatic, which is a completely different word, even though many confuse the two. What does adiabatic mean? Adiabatic means we have a system that will not share matter or energy. So when we create an adiabatic parcel of air, what that means is there will be no matter transferred inside or outside of that parcel, and importantly, no energy. It ain't gonna radiate.
Yeah.
So adiabatically, it will not share that matter or energy. Now, but why would a parcel of air become adiabatic? Now, not a lot of people know this, but if we create what's called a temperature gradient, so we need a temperature gradient or a density gradient with a parcel of gases. And at that point, when a parcel of gas changes its temperature by enough, it's only a couple of degrees, or it changes its density. How would it change its density near the ground? By the addition of water vapour. Then it says, it creates an invisible barrier around itself and says, I now don't like to mix with those gases which are a different temperature or density. I now don't like to mix. It doesn't mean I can mix. How do we mix it? Turbulence. If we have enough turbulence, we can't create that adiabatic bubble because we have continuous mixing of the air. Back to our parcel on the ground. If we have too much wind or we have too much air movement, then we can't properly form our adiabatic thermic bubble. So we need trees on one side, or a hedgerow, a house, or something like that to limit the air movement. So we need low wind environments or protected areas or fields which have trees around them to create our best thermic bubbles. Now, here's where this gets a little interesting. If we have our adiabatic bubble, as we know, with our hydrogen balloon and our helium balloon, that adiabatic bubble, as it gets warmer and changes temperature, it wants to go up. Also, it's a bit peculiar because if this changes in temperature, changes in density, then this should go up. As soon as it gets a bit lighter, it should go up. But it doesn't. It remains on the ground. So there's something that must be keeping it on the ground. What do you think it could be?
Connect to the earth or gravity?
So, a lot of people, or in a lot of the books or a lot of the suggestions in the general community, is there something called surface tension with the ground? Boom. You don't generally get surface tension with a solid. You can, but it's too rough. You're actually getting surface tension with the atmosphere sitting above it. So the atmosphere sitting above it, which it doesn't like to mix with, is holding that bubble on the ground. And that surface tension is quite difficult to break. Now, if you watch the high diving in the Olympics, I know you're probably an aficionado of that, and the curling in the Winter Olympics, you will see before they dive into that from a 10 metre height, they put a spray of water to break the water tension, the surface tension, so it's not like hitting a piece of concrete. Water is not just water. If it's not moving, it actually literally becomes a solid on impact. So to destroy that, they spray it with water. Now, we have the same problem here. Remember our hydrogen balloon? It didn't give a goddamn about that surface tension because it had so much power because it was so light. It had incredible acceleration. This bubble only has a degree or 2 or 3. It doesn't necessarily have enough power to get through that. But it does want to go up. It wants to get to what's called a similar density. The physics term is equivalent potential temperature. Don't be confused by that. Just say density. Let's say the same density is at this level of the atmosphere. That bubble wants to get there. It goes, I don't have enough power to break through that surface tension. Now, there's another problem with that surface tension and with this little bubble that wants to go up. There's something called drag. And drag is extraordinarily important. It's going to explain why these bubbles don't move as they should. Now, drag, we don't think much about drag when we have our aircraft flying. We think, oh, it's a bit draggy, it slows us down, shape, our this or that. Drag is massive and exponential moving through a fluid. I'll give you an example. Let's say we have a party and somebody goes nuts, as normally happens here every weekend. We get the entire big barbecue plate and we throw it into the pool. If you try to physically pull that barbecue plate up straight through the water, it is nearly impossible. If you flip it on the side, it will slip out easily. It will flip out easily. So you can see that depending on the size of the object, through that liquid or fluid, rather, gas, drag is exponential and significant. And if you ignore it, it's ridiculous. So if we take a weather balloon, that's going up, it's filled with hydrogen. Normally they fill it with helium so they don't explode with fire. When you do what's called your lifting gas calculations in physics in a hydrostatic atmosphere, discounting drag, so not including drag, that should go up, accelerating at 100 meters per second, which is literally, you're going to hit the speed of sound pretty quick. Obviously, weather balloons don't go up that quick. They go up at about 5 to 7 meters per second at a velocity. Why so? Because as the balloon moves through the air, it expands and creates enormous amounts of drag, keeping your speed there rather than that. The differential is caused by drag and it is significant. Now this becomes important for your thermic bubbles and why they don't budge. If that bubble is big enough, there is too much drag for it to lift off the ground. Think of your barbecue plate or a piece of corrugated iron trying to lift it out of the pool. It won't go. Turn it on its side, it'll slip straight out. You simply can't lift it. There is too much drag. This is important. Drag is critical. The bigger the pool of thermic air, the less chance it can lift off the ground. Back to our little bubble. It is held down by the atmosphere. It wants to go up. It doesn't have enough power, bit too much drag. It has a different route. This is sloping, as I pointed out before, and this will love to move up any slope, just like our balloon at the top of the ceiling will move to the highest point, or water will take the opposite route down a hill. It will take the shortest route it can to get higher. And on the edge of the bubble are trees, grasses, and things that will break the surface tension on the edge. And it will allow that bubble to walk its way up the side of the mountain. And this will happen most commonly in the mornings when there isn't enough heating that occurs to give it enough power to take off. It will be able to slip underneath the atmosphere with the left-hand side, in this occasion, being broken by turbulence caused by trees and bushes and fences and whatever the hell else, are tractors ploughing fields. Tractors ploughing in fields don't set off the thermal, they break the edge to allow it to move. And it creeps up here. Now, during the later afternoon or mid-afternoon, we have what's called flatland flying. Flatland flying because there is so much heat that these bubbles of air have enough power, like the hydrogen balloon, to go directly up. So with our heating of the ground through the day, we can see in the mornings, we will need to go to the edges of high mountains or spurs to catch those thermals that have been created early that are slipping up the hill. As the day progresses, we will start to find those thermals further out in the valleys or wherever they form because they'll have enough power to take off. And as the day cools down and progresses towards the later afternoon, they'll need to slip back up to the mountains. So we can't flatland fly until the ground gets warm enough later in the day. There is no point trying. Can't be done. In summer, in El Nino, with drought, the ground is so hot from the previous day and heating up so easily, this flatland flying could occur from 10 a.m. With La Nina and lots of rain and less heating, we're not finding it until 2 p.m. or further, maybe 3 p.m. to 4 p.m. So these things change depending on our heating, depending on our macro meteorology and our micro meteorology. So, if we're looking for thermals and we have to take a route from our mountain, then we know that those thermal structures will, if they can, take the shortest route to their highest point, as the water will take the shortest route to the lowest point. So if we look at this mountain up here from the east, we can see that there's some spurs coming out, and between each spur there's a valley. Now, we know this. If we wanted to look for water, we don't go to the top of the spur, we go to the valleys. And that's where we're going to find the collective water. And in contrast with our thermals will be rising up the edge of the mountain from those valleys or from the flatlands on the spurs. So when we take a route down that mountain, we will run the spurs, taking into account wind direction, where they can blow those thermals to find the thermals. If we catch a valley, guaranteed we will not find a thermal. This is a small version of alpine flying. You do not find thermals in valleys, you find them on the spurs. You must stay on the spurs to get enough height before you take a jump across a valley, because you can't find the thermal in the valley because it can't be there, just like the water won't be on the spur. It just won't be there. So there is no use searching for a valley or going across a low point. It's not going to damn work. So we must at all points have a flight plan before we begin to follow the high points down to this. Now, also what is important on the mountain here is we have a tree line, which then becomes complete fields. There's two aspects of that tree line. If we have thermals, which are forming here, heading up the mountain, when they hit that tree line, the tree line is actually where the flat lands stop. They didn't bother cutting the trees on the hills because they wanted the flat grazing lands for cattle or crops. So we have a double whammy. We have a 50-foot tree line and we have the land starting to rise up. And that is why we can find most likely thermals on a tree line here. It's not just a tree line, but it's a tree line and rising land. Now, when we're doing our flying, how are the XC boys doing this? We already know what the land is that we're flying along because we drive it. So we can have a look at it. From the air, it's very difficult to see where the bumps or lumps are. You can see the more significant ones, but you can't see the smaller ones. Now, what's important is if we look at those green tanks up there, they look about our height. They are 100 feet higher than us, even though they look the same height. Those tanks gravity feed this farm with the same pressure as the main pump from the river. So those tanks, even though they look level, are 100 foot higher. And if we look down to the river, you can see there's a significant slope. Now, you might come across the farm here and have troubles getting down. Why so? We're quite close to the river. If you look out there, the land there is actually lower. So any thermals formed there will creep here first. It's the easiest route first before we get there. If we look over there, the farm there is lower again, and so every thermal will head to here because it's the highest, nearest point. To get down, we go across to that field over there, or we go across to that field over there. To find lift, we go to the high point. To a normal person, it looks dead flat. To us, it's significantly higher. It's not just 1 or 2 feet higher, it's probably 50 to 100 feet higher, but it doesn't look like it. The best way to work it out is try to walk it. You'll feel it very soon, especially if you're unfit. So this is critical for what we're doing. So if we track across the mountain there, we can see that early in the morning, if we head into the flatlands here, guess what? We're just not going to find a damn thing. There is no point leaving it. The reason we go to the mountain is because all the thermals formed in all the land around here I'm going to go up that mountain because I don't have enough power to take off. So that's where I'm going. So if we're going to track early, we must stay with that mountain range. We can't fly flatland. There's a trigger point in the day when the land gets hot enough. It could be 2 o'clock, could be 11 o'clock, could be 3 o'clock. We can track across to the flatlands. But if we do the flatlands early, we must come down. There is no point in even attempting it. It simply doesn't work. So we can track along there. Now let's have a look at some of these other pools. Let's say we have a nice big area, 1 kilometre wide, of thermic air, which is say 50 metres high. Let's make it 70 metres high. This guy is very, very hot. In fact, stinking hot. And it wants to go up, but it cannot because there is too much drag. No matter how hot the damn thing gets, it simply can't lift off. Now, how do we catch a thermal from this? Let's say we have a tree on the side. That tree, moving about, breaks the surface tension and allows a feed of air to go up from that thermic pool. A paraglider that goes through a section of that pool can break the surface tension and allow a continuous thermic burst. The first paraglider coming into land, the others catching the thermal. The tractor working the edge of the field, breaking the surface tension, can allow another thermic funnel to rise from the same large pool of air which is continuously heating to fuel many thermals. The tractor working inside the field, the thermic bubble, will not disturb that nor create or allow a thermal to take off because we have an adiabatic section of air which is 50 to 70 metres high. This is adiabatic, not sharing itself. The tractor can only make a difference if it's on the edge, and on the edge it will make that difference. Now, with these different sections of air, let's have a look at another thermal. Let's go to general thermal theory now. This is the classic diagram in all the textbooks, and I'll begin with this because it is familiar. We have a core, we have different areas going up, like this. Now, our paraglider in this thermic structure is probably about this big. So we can see if we head into that thermal, we probably only have a 1 in 20 chance of running into the core. Now this is critical. Many people with this very large section here get into this section at 0.5 lift and start turning, and that's pretty good, and they're in lift and that's good, and they're too scared to leave that or search for stronger lift, and they'll remain in that. But that doesn't work very well when we're trying to do XC flying or just trying to have a good time. Why so? Let's have a look at Manilla. I think today, do we have a 3,000 metre cloud base? Let's say we'll just call, we need 3,000 metre climbs today. Let's say we're going to do low saves to 3,000 with a 3,000 metre climb, taking us to 3,300 metres or whatever the hell. Let's say we're going to get into a 0.5 metres per second climb. How long is it going to take us to do a 3,000 metre climb? Your answer is 6,000 seconds. Now, 3,600 seconds in each hour. Therefore, it's going to take you an hour, 45 minutes, give or take, to catch your thermal. That's quite a long time for a single thermal. If you manage to get to the core at 5 metres per second, 5 meters per second is 600 seconds or 10 minutes for your climb, which is significantly different to an hour 45. So bringing some maths into this, which many people hate, it is quite critical to understand that if we stay in our 0.5 lift, we're going to spend most of our day turning in circles, getting giddy and wasting time. If we stay in the air for 6 hours, basically we will report full thermal. And we won't have glided because we won't have time. So, that is why we must always be searching for a core. Now, there's another reason we search for the core. Just extend that way out.
Go for it.
Now, here is the next reason we need to get into the stronger parts of the thermal. We have the wind direction coming from here, so just to add, the strongest part of the thermal is pushed the least by the wind. If we have a look at those water spurts from the ground in city squares that the kids play in, the strongest, most accelerated part of the squirt goes the most vertical, and the droplets and little bits get dragged by the wind. The strongest part of the thermal has the greatest potential to reach cloud base. The weakest part of the thermal will have the least potential to reach cloud base. In fact, let's say our +5 gets to 3,000 meters, our +4 might get to 2,700 meters, our +3 gets to 2,500 meters, our +2 gets to 2,200 meters, our +1 gets to 2,000 meters, and our +0.5 gets to 1,700 meters. So when people keep talking about falling out of the backs of thermals, what they're doing is they're not actually falling out of the thermal. They haven't been in the strongest part of the thermal, which is the part of the thermal that will get to cloud base. They've been in 2 sections out, and that doesn't get to cloud base. So we must, if we are required to get to cloud base, which we must be, there's another reason as well, we must continuously search for the strongest part of that thermal, which is the part that is getting to cloud base. The other parts won't. Let's have a look at the wind. If we have an adiabatic parcel, what is critical is, remember, it will not share matter nor share energy. So the wind doesn't go through a thermal, it goes around. When we are circling within a thermal, we don't have problems with winds. We are within an adiabatic parcel, but with the weakest part of the thermal, which is bubbles and not very consistent air, that wind and the thermic structure will mix with turbulence and cause you problems and eventually be eradicated and only reach to 1,700 meters. So to be in the cleanest part of the thermal, to have the greatest speed and the greatest potential, all those things to reach the highest point, you must continuously search for the strongest part of the thermal and be in it, whatever that strongest part may be. Trust me, the lesser parts won't make it. Next, one of the reasons, as you can see from this very accurate diagram, is that if I'm flying and I have a 1 in 20 chance of hitting this thermal, if I hit any part of this thermal, one side of my wing will rise. And if one side of my wing rises, it tilts my weight shift to one side, it turns my glider away from the lift. When we train people, or when we start training people, their general complaint is when they've used an autodidactic approach, which is basically try again until you succeed, knowing nothing, is that they are on the ground every day in 7 minutes, and occasionally 1 in 20 times they run flat bang into the middle of a thermal and manage to stay up, but the other 19 times they go down. Why? If we have lift, it is guaranteed to put you on the ground in 7 minutes, because each time a lift on one side lifts your wing, it will turn you out and you will intuitively turn away from the thermal. We're flying this direction. On this side we get lifted, we turn away until we are on the ground in 7.5 minutes. The more thermic the air, the more likely you will be put on the ground if you do not know thermic theory. So, one of the important things here is that if our inputs are crazy and we move around and we shove around, we are not going to be able to feel the slight lift or movement of air. If we're listening to our vario because our vario is blazing, you won't be listening or feeling the lift of your glider. So as we fly, as we get lifted to one side, we recognize that and we bear with weight shift towards that lifted wing. Or lift, we bear to the side. Some days people are flying and instead of flying straight, you seem to be tracking to one side. The reason is you're tracking along the edge of lift because it keeps lifting you out of it. And we know if somebody's flying in a direction and tracking to one side, then all the lift and the thermic structure begins on that side that's pushing them out. So, when we're flying, we must also constantly not fly circles, but we must fly slight oblongs, or what do you call it, ovals, just for a second or two to one side, so we keep searching at all points for the stronger lift. This is a very classic structure. Let's have a look at it in reality, because only a few thermals look like that. On perfect days, once a month.